temperatures, high quality devices, this quantization can be in fractional value. This is the integer quantum Hall effect, and of course, if I go back to the previous slide, sorry, I can go into the fractional quantum Hall effect, okay, where these 1/3, 1/2, actually 2, 3, 4, 5, this is the integer values. How does the integer? Well, I can look at here is the density of state as a function of energy. Now, as I keep increasing the magnetic field, what happens is that the density of state at each lambda level increases, and I'm keeping the chemical potential here constant. So suppose I'm in a situation here where I have two filled lambda levels, the third lambda level is completely empty. In this case, as you know, my conductance is 2 e squared over h and my Rxx is 0. To understand why this happens, realize that when I have two completely filled lambda levels, my chemical potential lies in a gap. So in the bulk of the two-dimensional electron gas, there are no states in the chemical potential and no current can flow in the bulk. However, when I go to the edges of the sample, there is a confining potential which is keeping the electrons confined to the sample. This causes the edge states to curl upwards, and then near the edges I have the so-called edge states, which are now, because I had two filled lambda levels, I have two edge states on these both edges, and these are one-dimensional edge channels. Each of them has a conductance of e squared over h. Because I had two lambda levels, two edge states, the conductance is 2 e squared over h. And that's a simple single particle picture of the integer quantum Hall effect. But this is not the entire picture. Once I go to better devices, lower temperatures, higher magnetic fields, I can get into the fractional quantum Hall effect. And this is our data in graphene at the measure at 10 millikelvin, where you see that this is filling factor 3, where I have conductance quantized at 3 squared over h, Rx going to 0. But then you have all these fractional values, 7/3, 12/5, 13/5, 18/3. These are, you will see, these are all odd denominator scales. Why do this comes? Why do these things come? Because I have the single particle lambda levels, and then when I introduce electron-electron interactions, these open up interaction-induced gaps at fractional values of filling factors. And that's at those points again, because of the previously argued, and I will show you why. My gaps open up, my Rxx goes to 0, and my Gxy becomes quantized in nu e squared over h, where nu now is a fractional quantum number, a rational fraction, p by q. Okay? So what is the simplest picture I can have in mind of a fractional quantum Hall effect? Let's think of nu equal to 1/3 state. When I say nu equal to 1/3, I mean the conductance is 1/3 e squared over h. So in this case, the number of flux quanta in the system is 3 times the number of electrons. Okay? So the filling factor, it's the topological invariant of the system, and it is given by the ratio of the number of flux quanta to the number of electrons to the number of flux quanta. In the nu equal to 1/3, the number of flux quanta equal to 3 times number of electrons. What I can do in my mind, I can think of it as if 2 flux quanta I take and attach to the electrons. And I form this new animal where I have 2 flux quanta and 1 electron. Okay, it's a new quasi-particle, and I call it a composite form. Doing this, now I have taken 2 flux quanta and attached it to the electron. Now I have 1 flux quanta left. And this gives me the filling. So I have a strongly interacting electron plus 2 flux quanta. I convert it into a weakly interacting composite form. And I'm not going into the details, but the nu equal to 1/3 of the electrons you can think of as integer quantum Hall effect of composite fermions. So now let me go through all this because I don't have the time. So now this is the fractional quantum Hall effect. This is our data, and you see all these fractions coming at 1/3, 2/5, 3/7, 4/7, and so on and so forth. So when I'm in filling factor 1/3 of electrons, I have 1 flux quanta, I have 1 composite fermion per flux quanta. I will think of as the filling factor 1 of the composite fermions. When I'm in this regime, 2/5, I have 2 composite fermion per flux quanta. This is like an integer filling factor 2 of composite fermions. When I'm 3/7 state here, I have 3 composite fermion per flux quanta. It's like the Landau level 3 of composite fermion. So what I'm doing is I'm taking this strongly interacting system and trying to map it onto a non-interacting integer quantum power. So, and my objective in this talk is to show you how far we can run with this picture. At some point it must break down, okay, because I'm throwing out a lot of interaction in the system. So let's see how far we can go experimentally. And this is the so-called Jane sequence, 1/3, 2/5, 3/7 of the fractional quantum Hawking states. Now what about the bulk? Suppose now I'm in a state where my chemical potential is somewhere where the Landau level is half it. Okay, so these are my Landau levels. I have a large magnetic field, clean system, but I always have disorders in the system. And what the disorder does, it creates a long, broad states which are the disordered localized states. So at the center of the Landau level, which I call the critical point, I have some extended states, and then I have lot of localized states at the flanks of this. And this is the mobility edge. Now this is the most simplified picture of the Landau level which you can have. It's in some sense a very oversimplified picture. But for our purpose here, this suffices. So when my chemical potential is at the critical point, my Rxx is maximum, my Gxy is not quantized, and when my chemical potential is at one of these localized state, my Gxy is quantized and my Gxx is zero. So that's a simple picture of the quantum Hall effect. Now, as I can show you here, this is some sort of, as I move my chemical potential, I go from an extended state to a localized state and again to an extended state. So you can think of it like as if it's a localization-delocalization transition of a strongly interacting system. Now whenever I have a localization-delocalization transition, what do? From basic physics, basic solid-state physics, you know that there will be some exponents. For example, when I am in the extended state, my localization length is diverges. As I go further and further into the localized state, the electrons become small. The wave function localization regime becomes smaller and smaller, and then the localization length becomes smaller and smaller. And that is given by this parameter. This is the localization length, this is the filling factor, and this is a critical exponent which is the localization exponent. And that's the exponent that we would like to measure. And I will tell you why we would like to measure that. So, and of course, whenever you know that whenever you have a phase transition at the critical point, things critically slow down. So there is a critical slowing down of all your parameters, and that it's as if everything becomes very sluggish. And the time scales are given by this, the localization time dynamical exponent z, and that is another exponent that we would like to measure. So the temporal dynamics is determined by this localization exponent gamma. Spatial dynamics and the temporal dynamics is determined by this dynamical exponent z. And the ratio is called kappa equal to 1 by gamma z. This is actually the parameter which we experimentally can determine. So once I know these parameters, I really know whether it is correct to think of the fraction quantum Hall phase as a simple localization-delocalization transition. So how do we do that? Well, you try to do a finite scaling analysis. I will not go into the details of this. So you take this Rxy, you do a scaling analysis, and you can show that the derivative of the Rxy will go as t power minus kappa, where kappa is your scaling dimension, or you can take your Rxx and measure its full width at half maxima, and that also goes as t power minus kappa. So there are two ways of getting kappa. Kappa is 1 by gamma times z, and its theoretical values from numericals is 0.42. And that's what we start to measure. So, but recently there was a paper 2022 which shows that, which predicted that I should also see Anderson localization in the fractional quantum regime. That's a very surprising thing, because everything that I've spoken to you about is a single particle picture. And this is a many-body, strongly interacting many-body physics. So I'm not even sure whether it should work. So we just started out to measure it experimentally. So what we do, this is the fractional quantum Hall regime, and this is a previous result from Mansoor Sagan's group in Princeton, 2023 results. They measured kappa, and they see that the kappa is all over the place. The solid line is the expected value, and their values were all over the place. And they explained it by saying that, well, this is because this is in gallium arsenide. In gallium arsenide, you have very close to the 2D channel localized silicon defects. And these give long range Coulomb scattering. And of course, if you have a long range scattering, all your assumption of single particle physics, non-infecting picture goes out the window. So this is a collection of the data measurement of kappa over the last 30 years. And this line is the expected, and this is the data. So you could see we don't have a clear idea of what is going on. So we identified probably the culprit is this long range interaction, and the obvious solution is how do we remove it. So what we started, so there is a long range scattering. For example, as I told you before, in gallium arsenide you have these donor levels which give me long range scattering, and people found that when I could screen this long range scattering using by tuning the aluminum concentration, you could go to kappa, which is 0.41. Okay, so now that was the first thing, first parameter kappa. Remember there is another parameter gamma. How do I do that? Well, you do that, you extract that experimentally by measuring transport in this deep in the localized regime. Now deep in the localized regime, I am localized, so transport can only take place by variable wedge hopping. That is true for electrons. I do not know what fractions what's happening. I don't even know in fractions what is hopping. Okay? Whether these are anions, whether these are electrons, we'll come to that. So then you look at, so since this is a Frobisky kind of hopping, the conductance will go as T0 by D to the power half, and at the Fermi energy, a soft gap opens up, the energy scale is given by this, and here sits the parameter gamma that I am trying to get. So if I can get gamma, if I can know T0, I will get gamma, and this has been measured in gas, and gamma was 2.3 in agreement with theoretical calculations. So summarizing so far, there are scaling exponents gamma and z which characterize the plateau-to-plateau transitions. Results of scaling exponent in kappa inconclusive even in the integer quantum hall. No results on fraction, and no results of the localization exponent or the dynamical exponent z in the fractional quantum hall regime. So what do? We start off with our graphene devices, and our system of choice is ABA or Bernal stack tri-layer graphene. So there are 3 layers of graphene, and the second layer is shifted by 1 carbon atom with respect to the top and the bottom. And here is the band structure which we calculate using tight binding, simple tight binding method. And the important thing is that it has 2 kinds of bands. The orange one is a monolayer like band. You can see it is a Dirac cone with a small gap of around 1 MeV, and the blue ones are massive bands. And these 2 bands do not talk to each other because they are protected by layer symmetry. Now when I apply a displacement field perpendicular to this, the energy of this layer becomes larger than this layer. You break the mirror symmetry, and then these 2 bands hybridize, and you get something very devil's deep, very funny structures. So that's what we try to do. Okay. Now let's go to the results. This is our device. We have this graphite encapsulated HBA encapsulated high mobility ABA tri-layer graphene, and the mobility is around 40 meters square per volt per second, some of the best you can get in the world in tri-layer graphene. And first we start off our measurement on low mobility devices, where I did not have the graphite. So I have silicon dioxide. What does silicon dioxide do? Silicon dioxide has gangrene bonds which can trap charges, and that gives me a long range scattering potential which affects my transport in graphene. And when I measure this quantity drxy by d mu, the slope of it gives kappa. I get kappa to be 0.63, 0.50, 0.44, non-universal. Recall that the universal value should be 0.41. What's the culprit? Long range disorder potential. How do I take care of the long range disorder potential? I add a graphite between the substrate and graphene. So I encapsulate the graphene between relatively thick layers of graphite. It's a metal. So it screens of all long range interactions. When I do that, the expected exponent becomes 0.42, very close to the expected value of 0.41. Now I do the same thing. Of course, I do not stop at the first derivative. I can take the second derivative, which will go as minus 2 kappa, and the derivative gives me 0.43. Filling factor 1 to 2, 3 to 4, and this also beautifully gives me kappa equal to 0.41. Next, I go to the fractional quantum Hall regime. That was expected, nothing spectacular. We go to the fractional quantum Hall regime, and here is the raw data. This is a critical point. We sit here, and here are the drxy by d nu plots which we make. Integer, I get a kappa of 0.41, and interestingly for the fractions also we get the same value, 0.42. So we do it for very low, several different fractions. Of course, at very low temperatures you see the derivative saturates. That's because the samples are high mobility, the coherence length is very small, and at low temperature it's a sample size which limits the physics and no longer the temperature. So every physics that we see saturates below 100 millikelvin around. And so then we looked at from the width of the longitudinal resistance, we can also get a derivative of 0.41. Sorry if I'm running through this, but it's just a technique. The third thing which you can do is you can try a finite size scaling method. So you take all your data, RxY, which you measure at different temperatures, different magnetic fields, and then you try to collapse them on top of each other by varying this parameter kappa. And then you try to see where your collapse is the best. But visually it's not a very good idea. So what you do, you calculate an error, and the error here is on a log scale. So you try to find out the difference between the calculated and the experimentally measured values. And then you see that the error has a precipitous dip at 0.41, which tells you the critical exponent, the measured critical exponent is really 0.41. And when you do this, all your data at all temperatures, magnetic fields and electric fields collapse into a single plot. This tells you that the single particle scaling is working very well for the integer quantum Hall effect. So here is our data. This is the theoretical 0.41. And you can see that once we have eliminated this long range scattering, the data for all integer and fractions, they just collapse into a narrow band. So to compare, these blue dots are our data, and the rest of the thing is what has been observed over the last 30 years. That's okay. And what we have shown here is that we have proven that at least for the integers, it's a localization to relocalization transition. Previous measurements could not see because there's an artifact of long range scattering. Even more interestingly, it's also in the fractional quantum Hall regime that you have these localization to relocalization transitions, and they seem to be governed by the same set of dynamical exponents. So I will not go into any of this. How much? 2 minutes? Okay. So just to show you one last slide. In the gamma, so I have told you about one exponent, kappa. Now I have to want to get the other exponent, the dynamical exponent, which is z. So what do? I go to the tails of the lambda levels, and this is the gamma we extract for the fractional quantum Hall state, which is 2.3. So I think I will run out of time. We also have in this system very beautiful even denominator fractional quantum Hall states. That's what we are doing currently. With increasing displacement field in this system, you break particle symmetry, and so to summarize, integer quantum Hall and fractional quantum Hall transitions are governed by the same critical exponents. Okay, this is surprising because although superficially you can map one onto the other, integer quantum Hall is after all a single particle picture. Fractional quantum Hall is a strongly interacting many body physics. Scaling analysis validates the correspondence between fractional quantum Hall of electrons and integer quantum Hall of composite fermions, as we showed in the data. We observe non-abelian even denominator fractional quantum Hall states. I could not talk of it before, and we validate all the theoretically predicted all three: gamma, the localization exponent, the scaling exponent, and the dynamical exponent for the integer and fractional quantum Hall states. So these are the papers in case you are interested, and thank you very much for your attention.
So we have one question.
Hello sir, nice talk.
Thank you.
My question is that the electron and flux is getting somehow interacting together, right, sir?
That's the picture which we had, that's a mental picture which we had, yes.
Yes, sir. So then physically, how these flux and electrons are interacting? Means what is the basic physics?
So I don't think, look, as an experimentalist, I do not take this picture very seriously. Okay? There is no experimental, what can I say, evidence to show that how this happens actually. Okay? To me, it's just a mental picture which I keep to transform from, and the beauty is that it explains all the most of the observations of the fractional quantum theory.
Yes.
Okay, but if you are asking me microscopically, is there an electron and if there are two? So actually, these are not flux. If you are asking me whether these really flux quantas attached to electrons, I don't know.
Yes. So one more thing, that do we have any particular lifetime, that how long this will remain intact, and after that?
No, this is a ground state. So this is stable.
Okay.
This is the ground state.
Okay. Thank you.
So, but isn't there any particle quantum number for these things that can be measured? For
So
example,
the Chern number, that's the Chern number, that's the conductance.
Yeah.
but the chirality doesn't couple to the electron spinning there.
Very nice job. So, but is not that composite fermion theory ultimately, because essentially you are getting the non-interacting exponent, right?
Yes.
So it seems that this picture actually is working quite well.
Exactly.
So that's one comment. Second thing is that when you are extracting this far away from the mobility edge, this exponent gamma that's from the value across solve t. So how reliable it is, because you are far away from the critical point, right?
So yes. So the question which you are asking, if I can rephrase it, when I am far away from the critical point, is the composite fermion? So that's the question you ask. Is the composite fermion picture still valid? And so the question again, the question which you ask in this region is, what is hopping? Is it electrons? So think of the 1/3 picture.
No, even in the integer case, because you are extracting exponent far away from the critical point.
Agreed. But
There
the
are corrections to scaling and other things.
agreed. But that is the point where your transition is happening.
Yeah, but still you are like the transition is at the mobility edge.
I agree. There might be corrections. I agree, completely agree. There might be corrections. That's something I should think about.
Omik, it's a very nice talk. So I have a question that how much is the phase covariance length of the charge carriers?
So in this, say in the integer quantum Hall effect,
Yes.
it can be hundreds of microns. In the fractional quantum Hall effect, also they have an including my postdoc.
Yes.
You can go up to hundreds of at least few microns.
And what temperature?
10
millikelvin.
10 minutes.
And how much is the sample size?
So in graphene it's microns by microns. In gallium arsenide it's millimeters by millimeters.
Okay. And typically the mobility values, you said it's quite high. So
Yeah.
how
So for
much-
example, again in gallium arsenide the samples are around 40 million. In graphene the what best we can make is 1 million till now.
Okay. So, do you said that during the introduction part that while explaining the integer to fraction quantum effect, the transition you are explaining, you said that the Fermi level is constant, you are keeping it constant. Can you please elaborate that how you keep it constant or what is?
So what we do is, okay, there are two ways in which I can do the experiment. First, I can keep the number density constant, which will tentatively keep your chemical potential fixed, and then I tune the Landau level spectrum by using a magnetic field. Okay, that's the first way. Second way, what we do normally, which is preferable for us, is we keep the magnetic field constant. So the Landau level spectrum remains constant, and using a backgate, we change the number density. So the chemical potential sweeps through all the Landau levels. This is the preferred method because then you are not changing the Landau level, the magnetic length and all the interaction scales.
Okay. One last question, I'm sorry. You said that if you get better samples, then you can get even better fractional quantum
That's
effect.
right.
So can you please elaborate on the better samples?
Better sample in the sense of low. See, as I showed you this, there are all these disordered bodies. Now the fractional quantum Hall gaps are very small. They are around 100 to 200 millikelvin. If for the even denominator, for the 1/3, it's around 1 Kelvin. Okay, that corresponds to 100 micro electron volt. So if the disordered broadening is larger than that, then of course they get smeared.
Yeah. That's
So it's just disordered broadening, how much I have.
okay. Thanks a lot. Thanks.
So, yeah, the talk was very interesting. Just wanted to ask you, is there any evidence, experimental evidence of multifractal wave functions near the mobility agents?
In the integer there is, we have a paper. For the fractions, we are doing the measurements. I will let you know.
We can.
Okay, so thank you for this nice result. It's a nice discussion. So before we conclude this session, please, so Pawan Kumar will present this movement of it. So we have a tea break of 15 minutes, after which we will assemble.